Hello everybody and welcome back to another Flyout video. But it isn't really a Flyout video today, is it? Instead today, we are answering a rather unique question. So I was testing out ChatGPT for the first time today. Late to the draw, I know, but I wanted to try something rather peculiar with it. After asking a few questions about aviation, I realized how interesting something like this could be. So I asked questions. A lot of questions. And call me surprised, but it truly did answer back. Because of this, today we ask, can an AI truly build a fighter jet? Before anything else, we need a way of building this aircraft. In order to build this aircraft, we'll be using Flyout as a medium. Flyout is still in early development, but even then it's far and away the best building medium or simulator for this sort of project. I'll make sure to provide a link to the server in the description, and if you want to learn more about the game, please watch my previous videos. Anyways, let's get on to how I set up the AI for this. The very first thing I did with ChatGPT was to let it know what I was doing. I established a set of reference aircraft as well as a reference time period of the 1970s. This was to avoid any possibility of modern avionics or stealth, since the shaping and technology start to become inconsistent with modern knowledge. Knowing this, I then introduced a set of parameters, or rather, mission objectives for the aircraft that we were making. The parameters are listed as such. It needed to be Mach 2 capable, it needed to have an agile airframe, it needed the ability to carry 8 medium-range air-to-air missiles, such as like an AIM-120 or an AIM-7. Stealth for this aircraft was not a priority. It was to prioritize flight performance. It was to be operated by air forces, so no need for reinforced landing gear or arrestor hooks or anything like that. And ideally, this aircraft was able to stay airborne for long periods of time. From this point on, I told the bot it would need to make some design decisions in this aircraft, and that was to give me an answer when asked. After this, I was ready to ask my first question. The very first thing I asked was what the dimensions of the aircraft should be, and to my surprise, the bot gave me a pretty solid answer. ChatGPT had told me that the aircraft was to have a length of 15 to 18 meters and a span of 9 to 12 meters. This size is considerably average for an air superiority fighter of the class we were trying to make, so I was happy with this answer. Quickly, I set to work making the basic fuselage of the aircraft and moving the engines about 17 meters behind the nose. I say engines because I asked the bot how many engines the aircraft should have, and it told me in order to optimize power and redundancy, 2 engines should be used. It also told me that these engines should be about 4 meters apart from a center line measurement, and about 1.2 meters in diameter. All in all, that's more than 5.2 meters of this aircraft's width taken up by only the engines. GPT told me that this would be optimal spacing for weight distribution and stability. It also told me that this space would be sufficient for mounting air-to-air missiles in between the engines. This is true and has been used in real life on aircraft such as the F-14. Due to the size limitations of this aircraft, that would mean the main wings would be very small. I still wonder if this is solely because I gave GPT the F-14 as a reference aircraft, and the bot was following the engine styling present on that aircraft. Either way, the next suggestions GPT gave me differed far from any of the aircraft I had given it as a reference. Instead, what GPT gave me was reminiscent of an entirely unique aircraft, which definitely surprised me. GPT told me that in order to optimize airflow to the engines, and since we aim to achieve an aircraft that was Mach 2 capable, that a shock cone intake should be used. Every single aircraft I gave GPT was Mach 2 capable, yet all of them used ramp intakes instead of shock cone intakes. The AI explains to me that shock cones are ideal for compressing air at supersonic speed, and this is why it chose them. Either way, with a basic fuselage design in mind, and all the dimensions sorted out, we were set to start building. The aircraft would have a very thick wing area between the two engines, acting as the same sort of flat fuselage you see present in the F-14. This would also allow us to hold considerable fuel in that area, making for hopefully an impressive range. Next, I asked GPT about the wing shape. As we were in the process of building the fuselage, the wing shape for the aircraft was an important factor we needed to consider, so I believe it was a suitable question. GPT had answered that because of the speed of the aircraft, and the focus on high speed, that delta wings were suitable due to their increased lift under high airway, as well as their stability at high speeds. I also believed that delta wings were a good option as we didn't have a lot of width left to work with, and delta wings provided the most wing area with our very limited space. Regardless, in order to truly prepare for the range, we needed to ask the AI about the engines a little bit more in depth. We needed to know some statistics about the turbine engines in order to know how much fuel this fighter jet was going to consume. Keeping the previous constraints in mind, I asked GPT about the engine a little bit. First, I asked the AI about compressor stages. The number of compressor stages in a turbine is crucial to knowing the efficiency of the engine, as well as the tolerances, power, and fuel flow. This made it a suitable first question. GPT told me that in order to keep a good balance between complexity, power, and efficiency, that the turbine engine should have 3 low-pressure compressor stages and 8 high-pressure compressor stages. For those who don't know, this is fairly typical of a fighter jet's engine. The next question was about the combustor temperature of the engine. For those who are unaware, the combustor temp is directly responsible for the fuel flow in a turbine engine, while also being largely responsible for the power output. All things considered, this was a very important question. GPT had told me that the combustor temperature should be about 1800 degrees Celsius. This number is once again fairly consistent with what you'd see in a fighter jet. Lastly, I needed to ask the AI about the afterburner temperature for the engine. The afterburner is the fiery plume you see coming out of the back of fighter jet engines, and it's essentially a way for performance aircraft to generate a significant amount of power at the cost of a significant amount of fuel. The temperature, once again, directly contributed to the fuel burn and power output of the engine. GPT told me that for an aircraft of the given parameters, it should have an afterburner temperature of about 2200 degrees Celsius in order to provide the aircraft with the power it needs. With all the basics of the aircraft out of the way, I was ready to start construction on the rest of the fuselage. While building the fuselage, I let the nose/cockpit portion of the fuselage extend considerably down the tail. This makes for a more streamlined teardrop shape, as well as allowing me to store a little bit more fuel. This is very important for range and operating time, especially considering how much fuel these engines would consume in flight. The engine pods themselves would include an oblong bulge about halfway down them. I made this so the landing gear would have room to retract without interfering with the engines. Between the engines and the main fuselage, everything was connected using a very thick wing acting as a flat surface for mounting. Not only did this allow missiles to be mounted in between the engines, such as GPT had mentioned, but it also allowed for the majority of the fuel to be stored in this part of the fuselage and gave me plenty of room to work with fuel load. After setting up the inner fuselage of the aircraft to a point I was happy with, I started work on the wings. I was having to pay very close attention to the width of the aircraft in an attempt not to go over the limits set by the AI earlier. The overall wing surface was very small for this aircraft, and it would be relying almost entirely on angle of attack to stay airborne, especially considering the large flat underside present between the engines being the largest lifting surface on the entire aircraft. This, combined with the overall nature of delta wings and low aspect wings in general, showed that the aircraft was gearing up to have a very poor sustained turn rate. If you're unaware, sustained turn rate is a measurement of how well a fighter jet can turn under a constant turn without losing any speed or stalling out. On the other hand, an instantaneous turn rate refers to how fast a jet can turn without regards to any lost speed. Both have their own respective qualities in a jet fighter's performance. By my predictions at the time, this aircraft would have a very good instantaneous turn rate, but a pretty poor sustained turn rate. This is because the aircraft we are making has primarily low aspect wings and a focus on high speed agility. This means that the aircraft will be able to turn very well at high speeds, but it'll lose speed very quickly from turning. Now, we only have a few things to go before our first prototype can fly. Firstly, we need to add vertical stabilizers and landing gear. Earlier, the AI had told me that 2 vertical stabilizers should be sufficient, so I placed 2 vertical stabilizers over each respective engine pod. The landing gear of the aircraft is an unimportant factor to the airborne capabilities, so I simply quickly designed them myself. The last thing I asked GPT before our first test flight was if the aircraft should have a gun. The AI had told me that it should have a nose-mounted Vulcan-style cannon with 500 rounds of ammunition in it. With all that settled and out of the way, we were ready for our first test flight. This test flying phase is an important time where we get to make decisions regarding where we want to take the aircraft from here. More importantly, any problems we encounter, we can feed back to the AI for even more AI-driven decision making. Before we get into any of that, however, our first priority is to get off the ground and see how it flies. From that point on, we can test other, more physical characteristics the plane has. The very first thing I am noticing about this aircraft is how quickly it accelerates. It really pushes forwards with some ridiculous thrust, and I'm guessing this thing will also have a pretty high top speed. It also has very little fuel, and therefore probably a pretty small range too. Taking this first turn here, I am also noticing how sluggish the aircraft is in the turns. Not that it's super heavy or anything, I just feel like it could probably pull a few more degrees of AOA before stalling, and maybe we could get some more responsiveness out of it in the second test prototype as well. Also, just as predicted, it has a very poor sustained turn and rotor speed. Not much else is to be said about the aircraft at this point, so let's just skip ahead to the speed test so you guys can see just how fast this thing actually is. Alright, as you guys can see here, this aircraft is pretty quick. It's hitting about Mach 2.4 at the end of the test here. Also, something funny I noticed while I was here was that this thing can in fact super cruise. So this thing absolutely has speed under its belt, but it seems like we're going to have a few more factors that we'll have to work on in the next model of the aircraft. And with that, I guess we've concluded the testing phase, so let's feed those results back into the bot and see what we've got. With all the testing completed, it's time to feed this information back into ChatGPT. I told the AI both the pros and cons of the aircraft, and with that I had a new set of decisions by the AI to complete. With some modifications to the fuel tanks, wing area and angle, the addition of a flight control system, and a slight rework of the airframe, we were ready for the final product. And here it is, the final product. Mach 2.6 capable, ability to supercruise even with missiles and drop tanks equipped, Mach 1.5 on the deck, a 30 degree per second instantaneous pull, and a 12 degree per second sustained turn. This thing can carry 10 missiles and drop tanks. It doesn't just meet expectations, it exceeds them. Although one thing I must say about this aircraft, it is more of an interceptor than it is truly an air superiority fighter. It has very high top speed, very good acceleration, but not that much fuel and it can't stay airborne for long. I think in my opinion this classes it perfectly as an interceptor, more than anything else. Though the question we came to answer today wasn't truly what class of fighter jet this thing is, now was it? The question we are really answering today: can an AI build a fighter jet? Unfortunately for now, I believe that answer is going to have to be no. A lot of the components of this aircraft are designed by me, and the only way for them to really be transferred into this game is to have me decide some of the critical components and geometry of the aircraft. That being said, there is a lot to be told about the ability for the AI and the human to work together in a project like this. The AI provided a lot of very useful decision making and a lot of really cool ideas that I would love to see again. I feel like something like this can most certainly be improved upon in some way. Either way, let me know what you think in the comment section down below. I know this video is probably a little bit rough, so feel free to tell me what you think. Any improvements to be made I'll absolutely take note of, as I would love to do something like this once again in the future. Thank you all for watching, and I hope to see you in the next one. Goodbye.